So now that I've given you a quick overview of what an expression tree looks like when represented using algorithmic decomposition, let's go ahead and evaluate this in various ways. And we're going to talk about the benefits and limitations of this particular approach. And obviously, we're not doing this in isolation. The point of all this discussion is to compare and contrast with the pattern-oriented and object-oriented expression tree processing app case study we've been looking at for the past several weeks. So as I go through the pros and cons, think back in terms of how it was done when we did it with the earlier approach using patterns and objects. And I'll also summarize that at the end of the video series as well. So what are the benefits of an algorithmic decomposition? For certain generations of programmers, especially people who kind of grew up programming in the 70s and 80s, and even perhaps part of the 90s, this top-down divide and conquer based approach based on actions performed by the system is very intuitive to people who've been trained to think algorithmically. And this was really the way things were done for quite a long time. And it's quite amazing how much classic software, things like Unix or Linux, for example, is developed using this kind of an approach. Another thing about this that's arguably pretty straightforward, if you know this style of programming, is that the algorithm steps map clearly onto language features found in second and third generation languages. So things like structs in C, functions in C, functions in C++. In fact, there are actually some elements of generic programming and functional programming that actually share some of the properties of algorithmic decomposition in a lot of ways. So it's very familiar to people who are familiar with programming with languages like C and the data structures and processing capabilities provided therein. Another nice thing, arguably, that you get that's a benefit of this approach is you don't need to incur the overhead of virtual function calls. Everything is done just by making function calls. There's no extra levels of indirection here. We're not going magically through a V pointer to a V table to find the virtual function, invoke that virtual function, do all the dispatching. We're just making good old function calls. However, as is often the case with different design styles and approaches to building software, everything is not rainbows and unicorns. So there's, of course, some limitations with algorithmic decomposition that warrant our attention as well. And one of the reasons why it's so important to understand these things is to compare and contrast the algorithmic approach with the classic object-oriented approach, and more importantly, the pattern-oriented approach we've been covering. So one of the things that's a limitation with this approach is that the complexity resides in the algorithms rather than in the data structures or the structure of the app. And why that's problematic is that algorithms tend to vary, whereas structure tends to be more stable over time. Another way of looking at this is that the tree node data structure that we defined is passive. It doesn't have any operations defined on it. It's just a place to hold state, and all the real actions taking place in the functions that kind of rampage through that state and use it in any old way they feel obliged to or feel interested in doing. So there's no abstraction, there's no data hiding, everything's all completely up in the open and out in the open. And so any small changes, as we'll see shortly, break lots of stuff. Another classic problem, which is one of the things that object-oriented design and patterns have worked hard to overcome and eliminate, is the reliance on switch statements. Switch statements in Java, switch statements in C and C++ are fraught with peril. They have the obvious problem that they hard code you to a certain set of options, but it's also just accidentally complex. So it's very easy to make mistakes when switching on type tags. For example, you can forget to add all the cases, you can forget to put the breaks in the right places, and so on and so forth. So switch statements are very problematic. There's also another problem, namely incomplete and inefficient modeling of the application domain. The application domain, of course, here being the domain of expression tree processing applications and expression tree processing programs. And if you take a look at this carefully, you'll see that the data structure we have here, the tree node with all these unions and the type tags, end up with a very tight coupling between the nodes and the edges in our tree. So we're glomming everything together. It means that any small change affects everything, and it's just too tightly coupled for its own good from a design point of view. A dimension of this, or a consequence of this, is that we always end up making worst case assumptions about our tree node. Our tree node is used as the as the God class for everything. And therefore it's used for num nodes, it's used for unary nodes, it's used for binary nodes. And so we're always making worst case assumptions about the space utilization when we don't need to. In particular, the num nodes, which take up over half the tree in an expression tree, end up having to consume all the space for binary and unary nodes, but they have no children. So there's actually no need to do that whatsoever. There's also the classic problem that you always run into if you're not careful with languages like C or with C++ if you don't use structs correctly, to have little or no encapsulation. So all the fields, all the data members in this struct are exposed, it's naked, it's there for all to see, there for all to touch, there for all to modify and probably misuse. And that's a very common problem when you're trying to deal with data hiding in languages like C. There's ways to do it, but it's extra work, and because it's extra work and it introduces extra levels of indirection, people oftentimes don't use those techniques to hide the information. And so you can rampage through the state very conveniently, all too conveniently. Another more minor problem is that we use some macros here to simplify the use of the unions. And of course, anytime you use macros, you're just asking for trouble and you're polluting the global namespace. Another problem with lack of encapsulation and the lack of use of proper object-oriented design and hierarchical modeling of the design space is that any changes to this God struct, the tree node struct, will ripple through the entire program. So for example, we wanted to add a ternary node to our expression tree that's done with algorithmic decomposition. We would have to modify the God class, the tree node class, to add the capabilities for that, which of course would make things even bigger in the cases of things like leaf nodes. And then we would have to go laboriously through the software and make all the changes everywhere where we'd done switches on the type tag and add support for the ternary case. And as you can imagine, that's extremely tedious and error prone and just asking for trouble. So now that we've talked about the downsides with this particular approach, let's kind of put all the pieces together. So algorithmic decomposition yields top-down design based on the actions performed by the system. You can see here I have a bunch of flow diagrams, control flow diagrams, and data flow diagrams that show how the actions take place. And this particular way of doing things, which again is very popular historically, luckily not quite as popular now if you know what you're doing, it tightly couples the apps with specific requirements, which impedes reuse and complicates sustainment and evolution. So we end up basically programming ourselves into a corner, as I like to say. Extending the program to support new operators like ternary operators would require changes all over the place, changes to the tree node, changes to the various functions. And so it would just ripple through the whole program and make it much more brittle and error prone. So how can we overcome these problems? Well, the most obvious way to do this is to rethink how we model our domain, rethink how we design our code, rethink how we implement our code. And of course, as we already know by now, concepts and techniques like patterns and frameworks are crucially important in this process to ensure that the software you develop is going to be less coupled, more cohesive, easier to extend, easier to maintain, easier to port, and easier to adapt to new requirements and so on.